using the integral test. Why? Aren't there easier methods? Yes. But we want to see whether or not this series converges, so we need to show three things before we even get into the integral test. First, we have to show that it's continuous. And that's a rational expression, so it's continuous anywhere where the denominator isn't equal to 0. So we go, oh, denominator, where are you equal to 0? And then we solve that on down by subtracting that 1. Then you take the square root of both sides, but you're not going to forget the plus or minus. And then you see that that's imaginary, like your friends. So it doesn't have any real zeros. So it's continuous everywhere. Continuous, check. Next, we check to see if the function is bigger than 0. On that interval, of course, because that's the only one we care about. So we ask it, oh, function, where are you bigger than 0? When you're solving these rational expressions, you factor. Okay, it's fully factored, so then you put the zeros on a number line. You put the zeros on the number line. We're trying to see where n is bigger than 0, so we test a value to the left of 0. Why did we choose 0? That made the numerator 0. So to the left of 0, our function's negative because we just plugged in -1, man, and it worked. All right? And then we checked a number to the right of 0. We checked 1. Check, 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 check 1. And our function was positive because it had a positive numerator and a positive denominator. Now we're positive that it's positive from 0 to infinity. So because it's positive on 0 to infinity, it's positive from 1 to infinity. And then we check to see whether it's decreasing. We tried it in Spanish. But it decreases in English also. First we tried using series. But that got like seriously complicated because we weren't able to bound it. So we decided to go with derivatives. And bam, that's a quotient. That's low, d high, minus high, d low, all over low, low. And then we go, and we clean that up. In my numerator, I got that side. So, still, we're checking the inequality, and we put the zeros on the number line. We see the zeros, the denominator is never 0. So our zeros of our numerator were -1 and 1 because it factors like that. We chose to the left of -1, and we found that our signs were like that. And that gave us a negative value. And then we chose 0, and our signs were like that. And that gave us a positive value. And then we went and checked to the right of 1, and that gave us the signs of which gave us a positive value over there. Oh, excuse me. That gave us a negative value over there. Okay, but what did we care about? We cared where it was decreasing, and it was decreasing here and there. But more importantly, it's decreasing here, which is what we wanted to show. Okay, so then what did we do? We showed the three things that we needed to show in order for our integral test to even be used. So let's go use it. That means we're taking the indefinite integral from 0 to infinity. All right. That was improper, so we needed to switch it to limits. And we used fish for our variable. I didn't come up with it. They wanted it. We're in an actual classroom right now. So then, that was u sub. So we let u be the denominator. And then du was 2x dx. Look, our x dx is right up there in our numerator, which means all we got to do is divide by a deuce. Now we're going to integrate and then back sub later. So we put that 1/2 du over u. Naturally, we natural log to the absolute value. All of that was on the side. Because now we're going to back in our u back to our improper integral. So that's the limit as fish goes to infinity of 1/2 the natural log of the absolute value of x squared plus 1 evaluated from 0 to fish. So we do that fundamental theorem of calculus, upper minus lower. Now I ran out of room and that's why it's written like that. We just evaluated it. Now, my natural log of 1, that's 0. And look at that. When we put our fish in there, that's infinity squared plus 1, which is still infinity, and the natural log of infinity is infinity, so that integral doesn't converge, it diverges. So in conclusion, since the integral of the function diverges by the integral test, so does the series. And that's that.